In this video, I'm going to show you how we can use confidence intervals to run a hypothesis test comparing two proportions. Now, we used confidence intervals before to run a hypothesis test for one proportion. Now we're just going to run it for two proportions. And much like the hypothesis tests that use a p-value, oftentimes our conclusions will be the same. So if we reject the null hypothesis using a p-value, then we'll also reject the null hypothesis using the confidence interval. The main difference, however, is how we construct the standard error in the confidence interval. So when we use the p-value test, we construct the standard error by pooling the proportions together. But when we do confidence intervals for two proportions, we're actually going to keep them separate and we're going to keep our samples separate. So let's briefly remember how we calculate the p-value and z-score when we run a hypothesis test using this test statistic. Again, we pool together our two proportions to get our standard error that we called a pool standard error. However, when we construct confidence intervals, we use a slightly different standard error. You can see here that the standard error for our confidence interval is actually keeping the two samples separate. So we're using sample 1's p-hat and sample 2's p-hat and still accounting for those sample sizes. The fact that we use a different standard error means that occasionally our conclusions using the z-test versus the confidence interval are actually going to be sometimes different. But for the most part, most of the time, they're going to reach the same conclusion. So let's talk about how we can construct a confidence interval when we have two proportions. What we're interested in when we have two proportions is the difference between the two groups. So here I have sample 1, and I'm going to subtract off sample 2, and that's going to give me my sampled difference. Remember, we often think that that sample difference lies somewhere near the true difference, and so we're going to use our sample to try to capture where we think the true difference might lie. So we're going to reach up and down some margin of error. And again, this whole term here is the margin of error. It's the critical z times the standard error. We've already talked about how to calculate the standard error. We're going to keep our two proportions separate and account for our sample size to get that standard error of the sample differences. The critical z is the critical z's that you saw in the previous video. Hopefully you still have those written down and are quickly accessible. So again, those are the same critical z's that you'll see showing up in these problems. So let's go back to this problem that we saw when we ran hypothesis tests using the z statistic. Now, when we're using a confidence interval, we don't need to calculate the pooled proportion. We just need the two sample proportions. So these again are the proportion of women who have live births that are under the age of 38. You can see that's 28%. And for women over the age of 38, it's only 5%. So we saw these statistics before. And now, instead of pooling them together, we're going to generate our standard error based on these two different sample proportions. So our new standard error is going to be the square root of the proportion of the first group times its Q divided by the group's sample size. We're going to add to that then the proportion for group 2, which is the women over 38, times their Q divided by their sample size. When we do all of that, we get a standard error of 0.0431. Now quickly for reference, when we calculated the pool standard error in the previous video, we saw that the standard error was 0.056. So we do get a slightly different estimate for the standard deviation, and so that's why sometimes our conclusions can be different. But we're not making an assumption that the two groups are the same, so we're not going to use that pooled proportion when we create the confidence interval. The benefit of using the confidence interval is that you don't have to make any assumption about where you think the true difference is. So now we can construct our confidence interval. We start by calculating our sample difference. So our sample difference is just the difference between our two samples. So that's what I've calculated here to start as our midpoint. Then we reach down and also up to some margin of error. So our margin of error is that critical z, and if you remember, our critical z for a 95% confidence is 1.96. So that is given to you. And then we can use our standard error to complete the margin of error. When we calculate this out, we get a lower bound of 0.149 and an upper bound of 0.318. When we convert that to percentages, we can say that we are 95% confident that the true difference falls somewhere between about 15% to 32% more for women over the age of 38. So the 95% confidence interval can be interpreted as the difference between groups 1 and group 2, or in this case, women under the age of 38 and women over the age of 38. Because we put the women over the age of 38 first, that suggests that they have more live births, or their rate of live births is higher than women over the age of 38. This is because the interval is entirely positive. Because it doesn't run from negative to a positive number, the true difference cannot be 0. Here you can see that the true difference has to be positive. It's somewhere between 15 and 32. So if the true difference is positive, that means the group that you put first has to be greater than the group that you put second. So in this instance, women over the age of 38 is less than women under the age of 38. Or conversely, women under the age of 38 is greater than women over the age of 38. So because 0 is not in the interval, we can reject the null hypothesis that the groups are the same. We can say women under 38 have higher rates of live births than women over the age of 38. So the big thing to note in these problems is that the way that we run our tests is to examine whether or not our hypothesized value is in the confidence interval. When we're running a two-proportion test, our hypothesis value is always 0. So we're really just looking to see if 0 falls in this interval. That is, if it runs from negative to positive, or it's just completely positive. Here it's completely positive, so we can go even further and say that one group is greater than the other group. And that leads us to the conclusion as follows. We are 95% confident that women under 38 have live births at a greater rate than women over 38. Women under 38 have between 15% and 32% more live births than women over the age of 38. Now I want to make a distinction between the confidence intervals we did for a one proportion test to that of the confidence interval when we're dealing with two proportions. For the one proportion test, we're dealing with one parameter, that is where we think that true proportion lies. So if we create, say, a 98% confidence interval, then within that interval, there's a 98% chance that the true proportion is within that interval. So it's no more than 2.3 standard errors away from our sample proportion. So that's why we reach out up and down 2.3 standard errors to try to capture where we think that true proportion might lie. The difference between a one proportion test and then this two proportion test is that the two proportion test looks at the difference between the two groups. So in these second set of problems where we're dealing with two proportions, our new parameter is the difference between the two groups. So our new metric is this total difference. And our confidence interval then is based on where we think that true difference lies. There's a 98% chance that that true difference is about 2.3 standard errors away. And so we're going to use our sample and reach out 2.3 standard errors to try to capture where we think that true difference might lie. And so the construction of the confidence interval is really very similar, but our parameter of interest has changed. Our parameter here in a one proportion test is where we think that true proportion is. But when we're dealing with two proportions, our parameter of interest becomes the true difference between the two groups. So let me quickly go over a problem that creates a 98% confidence interval for the difference between two groups. Here, the two groups that we're looking at are those of a treatment group and those of a control group. So here, a company has invented a new drug called Nose-Its that they think cures acne. So they want to run a test to see whether or not they have evidence to show their new product actually cures acne. So they have 100 people wash their face with their product, and then they have another 120 people wash their face with the other leading brand. That's group B. And then they observe whether or not their skin clears up. And you can see that in group A, the Nose-Its group, they have a slightly higher rate of their skin clearing up compared to people who use the other leading brand. So yes, the rate is higher, but we also know that samples vary, and so maybe this difference is just due to sampling variation. Our standard error is going to account for that, and so you can see here I used my sample proportions that were separate, keeping in mind the sample size for each of those proportions, and then also the failure rate for those proportions as well. So we've calculated the standard error. We use the standard error then to construct our confidence interval around that sample difference. So the sample difference is really just 0.02. That's the difference between our two samples. And then we reach up and down some margin of error. This 2.326, that comes from, again, our critical z's. So this is a two-tailed test. So your critical z for a two-tailed 98% confidence interval is going to be 2.326. And then I calculate out these values for the lower bound and the upper bound. We can interpret the 98% confidence interval as where we think the true difference might lie between the two groups. So this first one is just for the proportion. We could also convert it to a percentage. So when we have a negative lower bound, it suggests actually that the second group has a higher success rate. They have more clean faces than the other group. Whereas when the term is positive, that suggests that the group that we put first, that is the Nose-Its group, they have a higher rate of clean skin. And so because this goes from negative to positive, that suggests that either group could have a higher rate of clean face, or that maybe there's even no difference between the two groups. So our data fail to reject the null hypothesis. 0 is in this interval, and our null hypothesis is that the two groups are the same. The difference is 0. And so we don't have enough evidence to suggest that there is a difference between these two groups. We have no evidence that Nose-Its is better at getting rid of acne. The reason why there's a difference between these two groups may just be because of sampling variation. So again, the way that we want to interpret this confidence interval is that we are 98% confident that the proportion of people with clear skin is 13.6% less for Nose-It users to 17% more for Nose-It users compared with the other leading brand. So The clear skin could be either less than or more than the other leading brand, or it could be the same as the other leading brand. It's not clear from this sample, and so we don't have evidence that there is a difference between these two groups. So that's how you construct a confidence interval. Remember that the most important part is in creating this standard error, that we're dealing with our samples separately. We're not pooling them together like we did for the Z statistics. This is because we're not making any sort of assumptions about where we think the true difference actually is. And so because we're making no assumptions, we're just using our samples separately. In the next video, I'm going to show you a few more examples of how we construct the confidence intervals, and then how we move on to interpreting and running hypothesis tests using that confidence interval.